Hello everyone, hope you all are doing great and safe at your end. Welcome to the day 5 of pre-hackathon speaker session. The Python week is hosting live workshop, talk, discussion and of course an amazing virtual hackathon. Everything which has already started on 1st Jan and ending on 10th Jan. Moving on the speaker session for today. The topic is modern image augmentation technique using TensorFlow API, and in this session you will get to know more about image augmentation and why it is useful with live implementation. And with that, let me introduce you to our speaker for the session. We have Ayush Thakur joining us. He's machine learning engineer at Weight and Biases. Hey Ayush, we welcome
Hello,
you
Manav.
Ayush and we are looking forward to your talk. The virtual stage is all yours.
Yeah, thank you, Manav. Am I audible to you and the audience?
Yes, correctly.
Perfect. So,
Thank you.
give me a moment for I start the presentation. By the way, hello everyone. As Manav mentioned, I work at Weights and Biases, and yeah, my task there is to basically create content and try to educate folks who are getting into it, into machine learning and working with really interesting tools these days. So today my talk will be about modern image augmentation techniques. We'll see into the implementations of these augmentation techniques and have a comparative study. The whole talk is designed such that you have a feel of how to basically understand a research paper, how to implement an idea, and then how to benchmark those ideas on a data set and basically compare and also compare different techniques to see which one is working better and which one is more suited to you. So uh, just a moment. Sorry for this. I guess my screen is frozen. Yeah. So for this talk, particularly for me, an ideal audience will be the one who have trained at least an image classifier. If you have worked with MNIST, have classified MNIST handwritten digits, that's good for me. You have some familiarity with image augmentation. You have an idea what augmentation is and all that. Something like flipping and random rotation. And you might have heard of tf.data API. This is basically API to build input pipeline for your model for training using TensorFlow. If you are not familiar with any of this, it's not an issue. I will have an overview, and the talk is designed such that even if you are not familiar with any of the concepts, you will have an desire to go into and search how to actually build a classifier or understand what an augmentation is or how to build a pipeline using tf.data. Uh, Going ahead, these are the resources you would like to check out. This talk is based on a weights and biases report, which I have written some months back. It's called Modern Image Augmentation Techniques. You can find the entire Git code as a GitHub repository, and the link to the slide deck is here. By the way, I will be tweeting this slide deck, and it will be shared in the Discord channel as well. Going ahead, these are the agendas of this talk today. Uh, we will just have a brief overview of what image augmentation is. We'll talk about how to build an input pipeline using TF data. It will be a code snippet, and I will just walk you through of how to use this API. Then we'll see what cutout augmentation is, then mix-up augmentation, followed by cut-mix augmentation. These are my three primary augmentation techniques that I will be talking about. If time permits, we'll go into augmix augmentation as well, and then finally we'll see how to benchmark all these augmentation techniques for model robustness. Uh, uh, If you have any question right now, you feel free to ask anytime in between. I will be answering those as well. Yeah. Going ahead, what do you have, like, what will you expect from this talk? So you will have a theoretical know of how different augmentation techniques work. And when I say modern, is because it's not if you are starting out, or if you are in an intermediate level of machine learning of being a machine learning practitioner, you might not have used mixup or cutmix in your normal training pipeline. uh, yeah, and we'll also see that implementation of these techniques in TensorFlow 2.x. We'll do some sort of interesting ablation studies. So if you do not know what ablation studies are, it's basically like you changing a variable and seeing what the effect of that variable is for whatever metric you want to evaluate on. We'll see some of those ablation studies. We'll do some comparative studies of these techniques. Finally, we'll benchmark the model trained with these augmentation techniques on CIFAR 10 dataset. Basically, CIFAR 10C is a dataset prepared using CIFAR 10, but the images are corrupted. I will show you the corrupted images when the time will be there. And then finally, we'll talk briefly about what model robustness is. Uh, so what an image augmentation is. If any one of you want to take a crack at this, you can maybe comment in the chat. Maybe the moderators will like to show that up on the screen as well. But on a very simple definition of image augmentation would be to introduce variety in training data so that we mitigate overfitting. Okay, so if you have a small training size, the data size is really small, and if you train a model, it will eventually happen that the model will overfit on the data, and you do not want that to happen. So that's one of the most popular use case of using any sort of augmentation. Augmentation is especially useful for images because it's been quite useful, and we have seen that as well. Some of the basic augmentation policies are mirror flipping. So basically, if you have an image and you flip the image from right to left or up to down, you can randomly rotate some of the images. You can zoom in and zoom out. You can blur the images. And there are a lot of such simple image processing techniques which we use as simple augmentation techniques. But for really high quality model, for really making the model robust to data shift or corruption, we might have to use some other augmentation techniques. This simple augmentation techniques might be good for simple data set, but it might not be really useful for a serious modeling of the data for any task. Quickly, overview of TF data. So it's an API which is used to build efficient input pipeline for training your model. We basically start with a base data loader. Okay, so you use a tf.data set, and if you have a array of xtrain and ytrain, you basically build this base data loader. We want our image to be pre-processed, right? So you want that image to be scaled in a range of 0 to 1. And then you also want the data loader to shuffle the images if it's used for training. So we are first shuffling the images, then we are applying this pre-processing step, right? We want batches of data, obviously, so we'll batch those. Then we'll apply, here I'm applying some sort of augmentation policies. The idea here is to show that you can map any sort of function to your base data loader, okay? And then we'll leave the prefetch and other stuffs because there's a lot one can look, one want to know when using tf.data. But again, if you want to learn more about it, I would highly recommend visiting these resources. So there's this YouTube talk by Saik Paul, and then there's this slide deck. So this will give you a good idea of how to use TF data. Again, so now it's time to actually get into the talk and see the various aspects of this talk. So Before we start, we need to first set up we first need to have an experimental setup, because all the models that we will train should have a baseline architecture. Here we will be using ResNet 20. Same data set, we will be using CIFAR 10 for training and validation, and then have some sort of assumptions or rules which will be throughout, so that we do not give some sort of biasness to any of the model. So we'll not be using any other image augmentation other than the augmentation strategy that is in question, right? And we will be using early stopping, because we all know that if you are training a model for n number of epochs, a model will eventually overfit on the data. So to terminate the model from training, we'll be using this regularizer called early stopping. If you're not familiar with early stopping, a simple Google search will do the trick. It's quite popular. Going ahead, this is the baseline model. So you can see that the best validation accuracy is around 77.74 percentage. You can see that the models quickly overfitted. The validation loss is going up while the training loss is still decreasing, a clear sign of overfitting. So we want to mitigate this, right? So we can use simple augmentation techniques, cool, but the stock is based with an assumption that you're already familiar with those augmentation techniques and you have used those things. But what's next? So one of the modern augmentation technique would be cutout. Even though it's quite old, it's 21 already. It was published in 2017 in this paper called Improved Regularization of Convolutional Neural Networks with Cutout. I will highly suggest that you read this paper. So what's the inspiration for this method? So we obviously want to avoid overfitting. So for doing that, we either use data augmentation, or we apply some sort of noise either to the activation or some sort of, or in the training parameters, etc. So one of the most common noise that we use is called dropout. There's this layer called dropout and Keras. It might is as well as in PyTorch. And you know that it's basically randomly dropping some of the activations during training, which discourages the adaptation of to some of the features. We do not want that. We do not want the model to stick with some features, and we want the model to try out different features. That's the idea. But dropout works really well with fully connected networks, but it lacks that same regularization power with convolutional layers. So then you may question why that is the case. So the authors of Cutout have these two explanations, which actually make sense to me as well. So they claim that convolutional layers, since they have less parameters, they do not require a lot of regularization from dropping activations randomly. Also, if you have thought about how convolutional neural networks work, it's basically all the spatial pixels in a local context share almost similar information. So dropping the pixel of a local, dropping a random pixel locally will not be of much use. So again, that's the reason why it's not such a good use. Dropout is not that adapted, and for that reason, we use batch normalization. Yeah. Another inspiration is from the autoencoders. So we know that autoencoders are good at learning useful representations. So if you know about autoencoders, there is a encoder network which basically encode the information in an image to a bottleneck, and then that bottleneck is used to decode or basically reconstruct the image in a self-supervised manner. There's various class of autoencoders like on context encoders, variational autoencoders, etc. Especially in context encoders, the input data is corrupted. So the task usually is to corrupt some portion or basically create some sort of patch in the input image, and the goal is to fill those patches with the best combination of pixels. So you can think that while doing so, the architecture have a much better understanding of the global content of the image. And it's highly useful for some of the tasks like maybe semantic segmentation or simply anomaly detection and all that stuff. So autoencoders are used for, we train an autoencoder and then we either use the decoder to sample more, generate more samples of the training example, or we use the encoder for any downstream task like classification. So from these two inspirations, the dropout and the autoencoders, the authors of Cutout actually made this augmentation technique, wherein they basically remove patches from an image, and these patches are removed from the input image while training. Okay, so any augmentation technique is applied generally while we train the model. uh, Again, all this inspiration and all those things might seem a bit, I mean, not necessary, because this is something which might be, we might think that is something very obvious, but having a theoretical understanding of why this is obvious is going to help all of us in the long run. So again, yeah, it's basically uh, can be viewed as a dropout operation in the input space, and it ensures that the model looks at, do not look at the entire image at once, but and do not focuses its attention on some part of the image, but but look at different like spatial features that are present in the image. So we understand how what's the inspiration of cutout. We have a cutout augmentation policy as well. You saw those, a batch of that image. So if we train a model, ResNet 20 in this case, and then compare with the baseline, you see that there's this improvement, even though the training loss is not comparable to the training loss of the baseline model, but we see that the model trained for much longer, right? That means that there's a good regularization that is been provided by cutout. Also, the validation accuracy is higher. Say this is the validation accuracy for the baseline, while this blue line is the validation accuracy for the model with cutout. And obviously, it's like some percentage gain from the baseline, and it's more generalized. How to implement this? The implementation of cutout is very simple. You just need to import this library called TensorFlow add-on. There's this method called random cutout, which takes in the image. You provide in the cut size, basically which is the size of the patch, and then you can simply pass in some constant values. So basically, how to fill that patch? You can either fill it with a value of 0, which is maybe blacken the patch, or you can have make the patch white, or you can have some sort of Gaussian noise as well in that patch. So the question is, if I am having this, if I have this implementation, this cut size, which here in this case is 10, 10, it is subject to experimentation. We can use any sort of cut size as long as it is bounded by the dimension of the image. So that calls for ablation study. So the authors of cutout basically said that the size of the cutout region is more important than the shape of the same. So you can have circular patches, you can have zigzag patches, whatever you want, but it's not that an important parameter. As important is the size of what you are actually cutting from the image. So here, for this ablation study, I am using 5 different cut sizes. These are 4, 8, 12, 16, and then 20. From this graph, you can clearly see that a small cut size, say 4, is not giving that much of improvement. The text accuracy is less than 77%. A cut size of 12 and 16 is giving a really good improvement, 80.5%. And again, a cut size which is like in 20 is deteriorating the performance, which is obvious, because if you are cutting only 4 pixels from a 32 cross 32 image, it's like irrelevant. You are basically removing nothing from an image. So that dropout inspiration is of no value here. And for a big cut size, you are basically removing all the information that is present in an image, right? You do not want that as well. So next augmentation technique that we'll talk about is mix-up. If any one of you have any question right now regarding cutout, you can ask here in the chat. If not, I will go ahead with mix-up. Yeah, so mix-up is like one of my favorite augmentation techniques because it's really simple to use and it's dataset agnostic. So for any of the augmentation techniques like flipping or even cutout and all these things, you have to be careful as to what to use and what not to use. Right? With mixup, it's really easy to use and it can be used with any sort of data, even it's text data or image data. So the inspiration is that uh, as you increase the number of parameters, uh, that is depending on the size of the data set. As big your data is, as number of parameters you will ideally want. Okay, and that means that your model might overfit on the data. Okay, which you do not want. So data augmentation is a process of training a model with similar but different examples, right? So we have the training example, but we do not just train on those examples, but we do some sort of transformations, either rotate a bit clockwise or anti-clockwise. So those are similar looking examples, right? So you can call this similar examples virtual examples, and you can think that these are being drawn from the vicinity of the training example. So if you like embed the whole training example in a 2D plane, right? Imagine embedding the whole example in a 2D plane. So from point A to point B, there can be a lot many examples, right, which you can draw, and those are the virtual example. So so again, so defining how to basically draw this these samples from the vicinity is again subject to your understanding of the data and what will work and what will not work. So a lot of human trial and error is required. So all the conventional data augmentation techniques, even though they improve the generalization of the model, but they have two issues. Issue number one is that they require expert knowledge, right? And the another one is that the examples in the vicinity is assumed that they belong to the same class, right? So if I have a MNIST digit 9, and if I rotate it such that it looks like 6, so you cannot do that, right? So you require to have an expert knowledge that you cannot rotate that image uh, like like upside down, right? And that if you do so, that's another. Basically, if you are rotating 9 of MNIST, you are saying that it's it's a virtual example which should belong to the same class as 9, which is not true. It's 6, right? So we have to be careful as to how to assign label to these augmented images. So what the authors of Mixup did is that they created an augmentation technique which is data agnostic. That means it's not dependent on the data, right? You can have any sort of data that you want and you can apply this technique. And this is simple. And the idea to create this virtual example is that, say you have two images, xi and xj, right? You add them with some weights, and weight here is the lambda. So you are taking lambda amount of x1 and then 1 minus lambda amount of x2, and then you are adding them to create a new image, and you are doing the same with the label, right? This lambda is basically a beta distribution. You want to have some sort of you want to sample this lambda from beta distribution because it enables that either you are having a value which will give more weight to x1, or at times you will have a value which will give more weight to x2. You do not want to have a lambda of 0.5 because you are basically taking half of like 0.5 of image 1 and then 0.5 of image 2, and if you add those two images, the images will be really unnatural. So you want to have like it should slightly lean to one side or another side. So this is the batch. You can see that even though it's an horse, there's something there inside it. For some reason, yeah, so this is bird, but it also seems like elephant is there mixed with it. So yeah, it's interesting. So if you compare this with the baseline, you can clearly see that the model trained for longer and the validation accuracy, or rather validation loss and the training loss, is not diverging. So it's kind of totally mitigating the overfitting problem that the baseline model had. So this model was trained with lambda of zero point 0.2. So yeah, so it we could train longer. That means the model is more generalized. You can see the validation accuracy is slightly better than the baseline validation accuracy, and the model training was stable, which is something that you would prefer, right? So what is mixup doing? That is something that you might question, because again, it's basically some sort of linear interpolation of two images, and then it's magically working. So what's happening, right? So model is encouraged to act linearly between classes, right? So by using this augmentation policy, the model is forced to act linearly between two classes. So if I augment a 9 and it looks like 6, instead of considering that augmented image as 9, it's kind of taking something in between, which is useful. I mean, this example might not strike really well, but just try to imagine that this like linear behavior is reducing this oscillation, which is actually visible in the validation curve. And then since you are doing some this linear interpolation, the decision boundary, which in the baseline model was like discrete, so like this is 1, this is 2, this is 3, this is 4, with mixum that boundary is bit smoothen out, right? So from 1 to 2, there's this whole space where the model has something to think about. um, yeah, again, the model trained with this augmentation technique will be more stable, obviously, in terms of prediction. How to implement it? Implementation of mixup is really simple. You can implement this in PyTorch as well, but here the example is in TensorFlow. So as you imagine that we are taking two images, so that means we will require two different data loaders to uh, from which we will sample one image at a time, right? So train loader 1 and train loader 2 are those two images, and they are both shuffled, right? And then we have applied this pre-processing step as well, which I've shown in the previous slide, right? So this mixup class, this function is taking two images, basically an image and label pair, right? It's then applying this linear interpolation. To do that, it's basically taking this L, which is sampled from this beta distribution. This beta distribution requires two arguments, alpha and beta. And the authors have used the same value of alpha and beta, and that is because if you see here in the graph, alpha and beta equals to 0.5 is this graph, right? This smooth graph going like this. And as I was saying, having this distribution means that at times a high value will come here, right, which will give more weightage to image 1, and at times a high value will come for this side, which will give more weightage to image 2. And that is something that we require if you think hard about it. Um, yeah. So now if you have two train loaders, 1 and 2, we are basically zipping them together using this dataset.zip method. So this, if you apply a mapping function called mixup, it is basically providing that image and label pair, two image and label pair to this function, which I have shown here. And then we will unpack the pairs, and then we'll apply this augmentation technique. Here you can see L into image 1 plus L minus 1 minus L into image 2, and that's your linear interpolation, right? Yeah, so again, the question is, we have this lambda or alpha, as you would like to say, and you would want to have some sort of understanding as which alpha is working better, right? So the baseline, the comparison that I showed was trained with alpha of 0.2, For this ablation study, I took 6 different alpha values. They are zero point 0.1. For some reason, the x-axis is not representative of what the actual value is, but this is zero point 0.1. This next value is zero point 0.2. This is zero point 0.4, 0.7, 0.9, and 1, right? And we can clearly see that the model train weight alpha of 1.0 is performing much better than zero point 0.2, right? So again, so what I'm trying to convey is that if you have any sort of technique or concept, you would want to do some sort of experimentation, and you would want to get the insight from the data that you are logging. And in this case, I can clearly see that the one that I took, zero point 0.2, is not working that good compared to 1, right? And I want that to happen. Yeah, going to cut mix. Before that, if you any of you have any question for mix-up, would love to have that. If not, let's go to the next augmentation technique, which is cut mix. Yeah, so this was proposed in 2019, right? So you might think that cut mix may be similar to cutout in some sense, and it's also mix, so maybe similar to mix-up. But you will see the inspiration real soon. So the previous augmentation techniques were unique and they work, right? They mitigate overfitting, they allow the model to be trained for longer period of time, improving the generalization of the model and all that. But when we are using cutout, it since we are removing a patch from an image, it is drastically removing, decreasing the portion of informative pixel during the training process. We do not want that to happen, right? So this since CNN is data hungry, so there's this conceptual limitation. Also with the mix-up, as I said, that if you mix two images, at times the resulting image might look unnatural and it might confuse the model, right? So cut mix is basically a solution to these two problems that cutout and mix-up have. So instead of removing pixels, what we'll do in cut mix is that we'll fill those pixels with not black or gray or Gaussian noise, but with a patch that we extract from another image, right? So in mixup, we are basically having this linear interpolation between two images. In cut mix, we also have in some sort of mixing of two images, but in a fashion that we are taking a patch from an image and we are putting that patch on top of another image, right? Again, this is really strange and it works. You might have questions as to why this is working. This also seems like we are losing on the information. But if you think really carefully, having a patch of all zeros, suppose this this is cat, right? If you have this all zeros in cutout augmentation, you are basically losing that zeros will not do anything with the kernel. Like a kernel multiplication with the zeros will result to 0. But here it's some sort of information which I mean, as I will show you, it will work better than cutout. Okay, and the ground truth labels in the mix-up, the labels were also linearly interpolated as the images. Here the labels are mixed such that it represents the maximum number of pixels that we have in an image. So for example, in this particular image, we have a car in the background, you can see, and then this cat that is like passed over this car. But we have a lot of information from this image, so the label is cat. Okay, so it's dependent on which image has the most amount of proportion in terms of pixels in this like resulting image. Yeah, so comparison with cutout. So again, why I'm doing this cutout, because obviously it will work better than baseline, but it will be more interesting to see how it performs in comparison to cutout, right? Because it claims to be better than cutout. So we can see that the comparison here, for this comparison, the cut mix augmentation use alpha of 1.0, right? And we trained the model, and you can see that Uh, Yeah, so this red line is the cut mix, and you can see that the trading loss is much lower than the trading loss for the cut out, but the validation loss is much lower than the validation loss of cutout, right? We see an improvement here. And also we can say that cut mix was much stronger regularization, because the training loss struggle in comparison to the validation loss, which is not the case, which we are not like used to this, right? Yeah, so it provides much stronger regularization. And you can see that the validation metric here, this red line, it was oscillating less than compared to the cutout. But then that's like my inference, and I think that that's because we have less informative pixels in the when we have trained with cutout, which might lead to this oscillation. Again, the implementation might seem a bit lengthy and like tricky, but it's conceptually very simple. There's this this function called getBbox is basically returning the top top left corner coordinates and uh, bottom right corner coordinates for the image, basically for the patch that we want to cut, right? And then this cut mix function is basically taking two images, same as mixup A and B. We are unpacking those images here. We are using this alpha and beta, basically again the beta distribution. We want to sample some lambda from this beta distribution, and this alpha and beta will be similar, same as mixup. Um, Yeah. So we are creating a patch from image 2 using this crop to bounding box method. You can look for a documentation. Then we are basically taking a patch from image 2. We are taking a patch from image 1, and then we are cleverly adding such that we have the resulting patch. Then here we are adjusting the lambda according to the pixel ratio. So the image that has the maximum number of pixels in the resulting image, the label is that image, right? So we are adjusting that lambda value here, and then according to that, the label is being mixed. Uh, Yeah, finally, again, we have two train loaders because we need two data loaders to have from which we can draw two random images, and then we are zipping them together and then shuffling them and then applying this cut mix, which is basically taking the pairs and then of adding this cut mix, right? So you can go to the GitHub repo that was linked in this slide deck, and maybe the moderators have shared that in the chat as well. And you will find all different notebooks which you can open in Colab, and then you can see all this implementation you can try out. So again, we have something called alpha, and then we want to do some sort of ablation study here, right? So this baseline model that I showed, this comparative model, comparison with a cutout, the model was trained with alpha of 1.0. Okay. When I did this ablation study, and in this ablation study, I used 6 different alpha values, same 0.1, this is 0.1, this is 0.2, this is 0.4, this is 0.7, this is 0.9, and this is 1. You can clearly see that the text accuracy for a model trained with alpha 1.0 is lower than the one that was trained with 0.1. So alpha of 0.1 gave best results. So that calls for us to have another comparative study with the cutout, because we want to test the best against the best. So we can clearly see that the model trained with cut size 0.1, this, I guess this is pink, is 1, and then this blue is 0.1. We can clearly see that the one trained with 0.1 trained for longer because it was better suited for this data set, and that we have a gain in the validation accuracy as well. Okay, so I guess we have some time. So we'll quickly go and see Augmix. But before that, I actually covered a lot, and I don't know if If any of you have any question, feel free to ask right now. I hope I didn't rush that fast with this. But again, I mean, we have this report that you can refer to anytime. You can read through this report, and that will give you a much better understanding of what I am trying to speak here. So let's go to the augmix augmentation. Uh, yeah, so cutout, we take a patch and fill that patch with any color, with basically any value. For mix-up, we basically take two images and then we do this linear interpolation. For cut mix, we take the patch, but we fill the patch with the patch from another image. And this linear interpolation is based on which image is contributing more to the resulting image. And then we saw this like improvement from cutout to mix-up and then to cut mix, right? But again, if you want to train a big model, right, it might happen that big models can learn these augmentation techniques. So large models might memorize fixed augmentation techniques. This random flipping, rotation, even cutout. These are fixed augmentation techniques, right? You want to have something which even large models with a lot of parameters cannot memorize, right? So one simple technique to do that is to chain multiple augmentation techniques. So like here's this original image with maybe change the color, we rotate it again. There's some sort of shear transformation, and this is the resulting image, which do not looks like same as the training image. We want to modify the training image, but we do not want to modify so that it do not even resembles a turtle, right? So image degradation is because of the chaining of different augmentation techniques, right? And this like sequential chaining is basically limiting to as to what we can use. So what augmex is proposing, and this is clever, we have this original image, we do some like from a pool of different augmentation techniques like auto contrast, equalize, posturize, rotate, etc., etc. We sample some augmentation techniques. So for example, here we have sampled three augmentation techniques: translate, rotate, and posturize. We apply the augmentation techniques to the original image. We then change those with another augmentation techniques. We cannot do. That is all. I mean, this whole thing is one of the combination that happened, right? It is a random process. We can have two augmentations applied to the original, we can have five applied to the original, we can have three in depth as here, we can have two in depth, or we just cannot have anything in chained with the modified uh, view of the original image. And then finally, after all this, we are mixing the original with this augmented image, and we have something which is, we even though we have applied so many transformations, but the resulting image looks similar to the original image, which is the idea of augmix, right? So I will not go into detail of how to like implement it because it's a bit lengthy, as you can feel. But again, at its core, it's simple. We have different images. We have an image. We randomly get different views, or rather different transformations of the same image. We apply more transformations or not. That is a random process again. And then we mix the augmented image with the original image, some sort of interpolation again, and then we train with this resulting image, right? So this is how the data, the augmented image looks like. You can see that there's like slight modification to the augmented, the original images in this batch. So again, we can compare this method with other methods as well. And here, this chart summarizes the augmix in comparison to all other methods. You can clearly see down here that augmix train for the longest amount of time. That means you have far more generalization. The augmix provided that much of regularization that it allowed to train longer. The regularization was not very aggressive, right? When we see the cut mix, uh, yeah, when I showed the cut mix, you clearly saw that the training loss was higher than the validation loss. That means it's a very strong regularization. With augmix, you see that this line, this we have like we started with strong regularization, but again, eventually at this point, the model started overfitting a bit. I mean, we do not call it a lot, do not call it overfitting actually, because it's not diverging. If we let it run for a longer amount of time, obviously it will diverge. Any model will diverge on the data. So again, it's far better. We have the lowest training and the validation accuracy. Similarly, we have the best training accuracy with augmix and the best validation accuracy as well with the augmix. It's actually beating all other augmentation techniques by a good amount of margin, anywhere between like 7 to 8%, which is great. We want that to happen. So we have all these augmentation techniques we discussed. We saw comparative study as well. We saw different ablation studies as to which parameters are working better for that data set and for that technique. And then we go draw some insight from the graphs that we could generate. But then there's this concept called model robustness. In real life, the data is not fixed. It's continuously shifting. There's corruption in the data. I mean, the data might not be preprocessed properly. There's a lot of issues with the data, right? So we want that the model, any sort of classifier, or any model for that, say object detection or semantic segmentation, etc., should be robust to these corruptions, right? So it's important that we benchmark the model that we train on a corrupted data, just to have a feel as to how it will perform in real world. To simulate that, I have used CIFAR 10C, which is a corrupted version of CIFAR 10. There are these 15 corruptions that we are interested in. So have a CIFAR 10 image and then apply Gaussian noise in that. Applies like pixelate those images, or this snowy artifacts, or we do some glass blur. So there are different corruption techniques. So we are using the same corruption techniques that the authors of augmix used, and then we'll see which model trained with an augmentation technique perform better on this corrupted image. Yeah. Before that, let's see how it performed a test. How do different models trained with different augmentation techniques like perform in comparison to the baseline? So this is the baseline model with 24.31 test error rate, right? And then this is cut out, mix up, cut mix, and augmix. We can see that augmix is far better than cut mix, then mix up, then cut out, and then baseline. So this is how it progressed, and this is how the talk was designed as well, right? But then this is on the test image. The test image is not corrupted. The test image comes from I can like let's say that the test image comes from the same distribution as the training image. It might be false, right? But again, the images are not corrupted. They are not distorted or anything as such. But in real life scenario, that will be the case. The images will be distorted. So how does different models perform on those corrupted image? And this bar chart, I mean, reveals everything. You see that the baseline model originally had 24.31% error rate. On a corrupted image is 39%, which is close to like 40%. This cutout augmentation 40, cut mix 37, mix up 37, and then this cut mix is 40. So all the augmentation techniques that we like talked, and then I said good things about them, they all perform really bad on this corrupted image. Actually, your cutout and your cut mix perform worse than the baseline, which is, I mean, interesting. But at the same time, if you see augmix, it's 22% test accuracy, the error rate, which is kind of half of what the baseline is performing, right? So even though, so training with augments showed that this augmentation technique is far suited for training a classifier or any for training a classifier for a classification task, and then deploy that model into production because it will guaranteed perform better than other augmentation techniques, right? So that's the whole story here. Here, this chart basically shows how the model is performing for different noise, for different corruptions compared to the baseline. This blue is baseline. So we can see that for almost all the corruptions, Augmix is performing like far better than the baseline, which is something that we want. So I guess that's it for my talk. Discuss about different augmentation techniques and show different ablation studies and then compare them, and finally your augmix is working better. By the way, this is how your CIFAR 10C looks. So you have this board, and then for that board you have distorting the board using different augmentation techniques. Here we have some patches, here we have some apply some noise, we are blurring here. So there's this different level of sensitive, different level of like degradation which have been applied. There are 5 levels, and the scores that I've shown here, they are average across all the different levels. Right, you will want to check out the GitHub repo. By the way, if you have any questions now, you can formally ask them, because yeah.
Thanks a lot, Ayush. It was indeed a great session and had a lot to learn. If we have some question, just check. We have one question from Mamik Patel. What are the best resource to learn TF?
Okay, so best resources to learn TensorFlow would be, I mean, to be very honest, one of the finest resource or the finest thing to do is to basically go through all the tutorials that Keras has. Uh, yeah, these tutorials are really good. You might want to check them out. Even TensorFlow have their tutorials. Uh,
Yes.
Going through them will really help you get a grasp. Maybe if you can afford buying books, go for it. Books like Hands-on Scikit-learn and TensorFlow, those books are really good. Yeah, for me it was more like I just took a task, say classification, and I learned all there is to learn for that task. So blog posts, there's abundant of content available online. You just have to choose from the best. And like
Yes.
going for the official stuffs, like the tutorials by Keras or tutorials by TensorFlow, they are really good. Even Bitmouse is good.
Great.
Yeah.
So we have one more question from Pratin Kundu. Does data training for data augmentation take more time to train? If yes, why so?
Yeah, obviously, if you train your model with any sort of augmentation techniques, that will take longer compared to a baseline model, because because your CPU is doing those transformations on the image and then providing the image for training. But the fun part about TF dot data is that it's meant to form efficient and high performing pipelines, input pipelines. The answer is yes. It will take time, no matter which augmentation. If you even apply a random flipping, there will be some millisecond, like more time to train compared to
Yes.
baseline. Yeah.
Yes. Great. So we have one more question from Het Suthar. How we can identify whether our model has underfitted or overfitted?
Yeah, good question. Let me show this
Yes.
real quick. Yeah, so you can see that. Here, the training loss is decreasing while the validation loss is still increasing. I mean, it's diverging. So whenever you look at your plot, the metrics plot, and you see that your validation metric is diverging from the training metrics, that means that your model is memorizing on the training data, but it's not generalizing across the data, right? That's why your validation accuracy gets bad with time.
Yes. In chat section, I think now we don't have any question unanswered. So, okay, one more from Pratibha. What is 1 dB and why it is required? Actually,
Okay.
I don't understand it.
Okay, good question. So, if you are training models, I would like to frame this way. You are basically developing software or some project. You use GitHub to maintain the code. You basically have this version control of the code that you are writing, right? Similarly, with model, you want to have some sort of version control, because if you train a model A, you want to know which data set was used to train that model, right? And if you train different versions of the same model using the same data set, you want to like do this comparative study. I mean, we are logging different things here. If we have not used any sort of machine learning tracking tools, metric tracking tools, we will just fail to grasp the insights, right? And that's where weights and biases come in really handy. You can like easily, it's easy to use with any framework. You can simply like just a few line of code and you can have all the metrics logged, and then you can have these insights. If you if I, as I showed in the ablation studies, if I trained a model with alpha 0.2, but it turned out that alpha 1.0 was better, and that was
Hmm.
because I trained models with different alphas, and then I saw the bar graph for the test error rate, and I saw that alpha 1.0 is performing better. If for all these like insights, you want to use some sort of machine learning like metric tracking tool in your workflow, it's a good practice, and this is a practice that's used in the industry. So getting a habit of it is really good. You might want to try this access. It will be easy to use. You can read out this report, go to the GitHub code and just run the Colab notebooks. It will just, hopefully it will run out of the box, and then you will
Yes,
have the feel like after a few times.
yes, exactly. So now we have one question from Hitsuthar. Do we have
Do we
any
have any
predefined value for
predefined?
lambda?
No. Again, the authors have like for a data set, say CIFAR, the authors might have said that alpha or lambda 1.0 works better, but then that's subject to experimentation. You have to experiment it out. There's no hard. It's like a hyperparameter, right? So what batch size you want to train your model with is something that you will experiment with. That's the same with lambda.
Okay, nice. So one more question from Mamik Patel. I know somewhat data visualization and some statistics. Still, I'm in SEM 1. Can you guide me? What can I learn next? Want guidance?
Right. So if you are familiar with some sort of data visualization, that means you have worked with Matplotlib and all that thing. And if you are familiar with statistics, I would say that mm, again, I mean, I might take time to frame this question well.
Yes.
The next thing to learn is maybe have some sort of course. I will highly recommend Andrew Ng's Coursera course, or go for SendText. That's a YouTube channel. You can learn few things there. So yeah, or just read some articles, read some blogs. You will eventually have a line like a guide for yourself
Yes,
as to what to follow and what not to follow.
exactly. So I think now we don't have any question unanswered in chat section. Okay, so some of the participants are not live right now, but surely they will have full access to our recording. Guys, later on, if you have any question, feel free to ask in Discord server. There is one channel, Ask Speaker. You can ask there your doubt to our speakers. Okay, so Ayush, I have one question from my side.
Okay.
Okay, as you know, we will be hosting the 48-hour hackathon. Do you have anything you would like to suggest our hackers?
Regarding what will be they hacking on? What's the
Yes,
agenda?
exactly, exactly. For what we do with this in hackathon.
Yeah.
So actually, we have a 48-hour hackathon at the end of 7 days workshop. So according to our today's session, they are uh, they are using these things. What you can explain in previous hackathons. So I want suggestions from your side.
Okay, so since I am into machine learning, and if any team will be working with like building something which involves machine learning at its core, I would say that take things like, I mean, work start from a simple baseline and with some easy to make model, something which you can like quickly implement, right? Do not start with something complex, something hard to use, or if you do not have an understanding of those things, leave those things for a hackathon. In the context of hackathon, start with something simple. If you have a baseline, like build everything around that baseline model, all the pipeline. If you have some, if you want to build a server, if you have some website to like client facing front end, build everything on top of that baseline. That will be a good point of proof of concept for whatever you are building. And if you have
Yes,
time, try to improve the baseline. Use, I was really suggest to use some sort of tracking tool. Again, like me talking about race and basis will sound like me promoting it, but I love it, so you might want to try it out. uh, to improve the baseline, see what's working, what's not working, and then with small steps gradually improve the baseline so that you have much better chance as winning that hackathon in the with your tech. Yeah.
yes. There were some valuable suggestions from your side. It would be a great help for hackers. Thanks once again for joining us today.
Yeah, thank you.
Thank you. So guys, also do fill the feedback form shared in the chat section, and it will also be used to assign the certificate for this session. It will be open for only 15 minutes and will not be reopened again. Thanks a lot everyone for joining us. We have one filler session for the in the next 15 to 30 minutes, and after that we have one more session at 5 p.m. IST for a live intro to PyTest. Hope to see you in the next session. Stay safe, take care, bye bye.